Okay. All right, today we're going to be looking at Chapter 8 Extension, Mathematical Induction, okay? Mathematical induction is a method of proof. I know you guys missed proofs from geometry. So remember in the first section, when we were writing an expression for the apparent nth term, basically like the explicit rule of a sequence, what we did is we kind of assumed that just because we saw it was true for the first couple, that it would be true for all of them. But that really is not a logically valid method of proof, okay? What we kind of want to do is have like a better foundation. Now, obviously, in those cases, you're not going to need to use mathematical induction to prove every time that you do that. But we want to go through this process so that you have that idea down. All right, so let's consider this series. 1, 3, 5, 7, and series means that we're adding them together. Okay. Let's write a rule for each term. Okay, so these would be the terms of this sequence. 1, 3, 5, 7. So first, is that arithmetic or geometric, or neither? Arithmetic. So let's use that to write a specific rule. Based on the work we've done, what would that rule be? 2n minus 1. 2 is our common difference, and our a sub 0th term would be -1. Okay. So the first term is 1. What is the sum of the first two terms? 4. What about of the first three terms? 9. The first 4 terms? 16. The first 5 terms? 25. It appears that there is a pattern, correct? And that pattern, if we made that assumption, what would the rule for the sum be? That the sum of the first n values could be given as n squared. Good. All right. So we noticed a pattern for each partial sum. And even though based on the work we did here, we know that this is true for the first 5 partial sums, we don't know if this rule is going to be true for a partial sum that has 1 million numbers or n numbers. And so what we need is we need something to kind of justify that. Because yes, it's true for the first 5, but how do we know it's going to be always true? So that's where we get to this idea of this method of proof called mathematical induction. It can be used to prove certain formulas or conjectures. It depends on a recursive process that is much like climbing a ladder, okay? First, what we're going to do is climb onto the first step, okay? And if you can climb onto the first step, you're good. Then what we need to do is show that we can get from the first step to the second step. Now, if you've gotten to the second step, can't you get to the third and the fourth and the fifth? And that's what we're going to do. So first, so this is the steps that we're going to use to prove a result by mathematical induction. First, we're going to verify that S sub n is valid for the first possible case, usually n equals 1. Okay. Then what we'll do is we're going to assume that S sub n, that the sum, the rule, is valid for some n equals k. So this is like a random rung on the ladder, is this S sub k. And then what we're going to do is we're going to add the next term to it. So we're going to add a sub n, k plus 1 to that. If we were looking at S sub k, that means that we added everything all the way up from a sub 1 to a sub k, and we got S sub k. Well, now let's add one more term to it. Let's add the next term, a sub k plus 1. And if we add that to it, then that should give us S sub k plus 1. Okay. So again, we're trying to go from one rung of the ladder. We're going to assume that it's true for S sub k. And then Okay, let's add the next term, a sub k plus 1. So we're adding a sub k plus 1, which is the next term. And then if I add the next term to s sub k, then that gives me the sum of everything, including that k plus first term, okay? Now I know that this is assuming that s sub k is true, but since s sub n is valid for n equals 1, then we've shown that it's now valid for n equals 2, and n equals 3, and n equals 4 because we use this generic s sub k. So for all of this to work, we have to be able to find, that shouldn't be there, to find s sub k and s sub k plus 1 given s sub n. So we're going to show that s sub k, which is the sum of the first k terms, plus a sub k plus 1, which is the k plus first term, is going to equal the sum of the first k plus 1 terms. So we're going to show that that is true. So we're going to have an expression for this on the left, an expression for this on the right, and we're going to show algebraically that that's true. Now, when working the proof, remember, just like when we were verifying identities, we should not cancel like terms on both sides of the equal sign. However, you can simplify both sides until you have the identity statement. Okay. So we're going to do 5 of these problems together today. Right? In our first example, I'll write kind of like what we're doing on the left, and then we'll actually do the process, okay? So if I'm have here s sub n equals what we just talked about, 1 plus 3 plus 5, etc. And here we said that this 2n minus 1 was our rule, and that n squared would be what we do for the sum. Okay. So the first thing we're going to do is show that it's true for 1, which means we're going to show that the rule at 1 equals the sum at 1. Essentially, we're going to show what happens when n equals 1. Okay. So let's put 1 in here. 2 times 1 minus 1. And let's put 1 in here. 1 squared. Well, 2 times 1 is 2. 2 minus 1 is 1. And 1 squared is 1. Well, that's nice. Okay. Now, just FYI, when I say that it's true for 1, it doesn't have to be 1 equals 1. It could be like 5 equals 5 or 6 equals 6 or something like that. You're just putting 1 in and you're getting an identity statement. Okay? Next, we're going to assume that s sub k is true. What we're going to do there is put k in for n in the sum part. Okay? The s tells us we're dealing with the sum, right? Okay? And so s sub k means we're just going to put k in for n in the sum part. So we're going to assume that s sub k equals k squared. So put k in for n in the sum part. So the sum part was this part, right? The n squared part here. So put k in for n in the sum part. So because our sum was n squared, we're going to replace n with k. That's k squared. This next part is kind of organizational. We'll see this as we go forward. then let's put what S sub k plus A sub k plus 1 is going to equal. We're going to use the S sub k that we just found, okay? Then we're going to put k plus 1 in for n in the rule part, because A sub whatever tells us our rule. And if we said A sub 8, wouldn't we replace the n with 8? So if we see A sub k plus 1, that means we're going to replace the n with k plus 1. So let's bring the S sub k down. We said that that was k squared. And then our A sub k plus 1, we're going to put k plus 1 in here. So my rule is 2n minus 1. And again, in for n, I'm going to put k plus 1. Okay. So there's S sub k plus the A sub k plus 1. Now let's organize what S sub k plus 1 should look like. In this part, you're going to put k plus 1 in for n in the sum part, because we're looking at S sub k plus 1. So S means the sum. K plus 1 means that we're going to substitute the k plus 1 in for n in the sum. So then that would be k plus 1 squared. So we had some of this organizational stuff on the left. Now we're actually able to put that in the proof. We're going to say that starting, if I'm at this rung of the ladder, k squared, and if I step up 1, the A sub k plus 1, which is going to be 2 times the quantity k plus 1 minus 1, I want to show that that's the same as what I said my sum was squared, the quantity k plus 1 squared. And I'm going to show that those are equal to each other. Okay. Usually we leave the right-hand side mostly the same. You'll see some minor variations as we go forward, but we're doing that the same because we want to show that this is like this n squared, this k plus 1 squared thing, okay? So let's work on our left, and we could distribute. So what does that give me? 2k plus 2. And then we could combine like terms. We get k squared plus 2k plus 1. And what could you do to that? Factor it. And how does that factor? Oh my gosh, that's what we wanted to show, all right? So the nice thing about that, kind of like the same thing with the verifying identities, is that you know what you want to get to, right? So we found that and we're good to go. I'm going to be 100% honest. In a quiz test situation, I should have modified the worksheet. That's my bad. These steps are not all going to be on there, okay? And as we go forward, this is kind of like what I would want to make sure that we have on the test. You don't have to write like all the words out, but basically the first thing you're doing is you're showing what happens when n equals 1, right? That's the first thing that we're doing. We're showing what happens when n equals 1. The next thing we're doing is we're assuming that S sub k equals k squared. That's the next thing we're doing. And then the last thing we're doing is we're proving that this is true. So if you get to the point that you don't need to do that organizational stuff on the left with the, in my green and blue here, that's fine. But essentially, those are the 3 things in the mathematical induction that you would need to do. This is just kind of helping us get organized to put them into this piece, okay? So if on your worksheet you don't have these, but you can, if you want to put these right here and here, that's fine, okay? If you're struggling with that, use the prompts on the left until you're able to get to that point, okay? But that's the process of mathematical induction. We show that it's true for n equals 1, assume that it's true for s sub k, and then prove that if it's true for s sub, we're assuming s sub k is true, I'm going to climb a rung of the ladder by adding the next term, and then that should equal the rule of the next term, okay? So let's try a different one. S sub n equals 1 plus 2 plus 3 plus 4 plus 5, blah, blah, blah. And it tells us the rule, but it's pretty obvious that our rule is just n. And that our sum is this n times the quantity n plus 1 over 2. Okay? So let's show that it's true for 1. Okay? So when n equals 1, 1 equals 1 times 1 plus 1 over 2. So 1 equals 1 times 2 over 2. My 2's cancel. 1 equals 1. We're good to go. Okay? So what that means is that I can get on the first step. That's what that means. I can get on step 1. Now we're going to just say I'm on a random step. S sub k is going to be k times k plus 1 over 2. So I'm assuming that then that is true for a random step. I'm on a random step. The sum is k times k plus 1 over 2. So now I'm on that step, take k times k plus 1 over 2. But now I want to step up. So to step up, I'm going to add another term, which means I'm going to need to add this rule. But I want to add the next term. So that means I'm going to replace that with k plus 1. So then s sub k plus 1 means that I can replace this sum here with k plus 1s. So k plus 1 times k plus 1 all over 2. Okay. So I'll be very literal in this one. So here I got k times k plus 1 over 2 plus k plus 1. And then here I got k plus 1 times k plus 1 all over 2. And I want to show that those two things are equivalent. Okay? I know I said to leave the right alone, but there's something that's bugging me about the right. What do you think it is? Plus 1 plus 1. By all means, put those together, okay? So by all means, turn that into k plus 1 times k plus 2 over 2. Again, I was just being very literal when I had the k plus 1, but in reality, that's best thought of as k plus 2. Okay? So we should probably put this over 2 also. Okay? So I'm going to have, I'll say k squared plus k. Let's just say that you decided to distribute. And then I would need this over 2 as well. So what is k plus 1 written over 2? 2k plus 2. So you multiply k plus 1 by 2. Basically, you're multiplying by 2 over 2. And now I have a common denominator. So what would the numerator then become? K squared plus 3k plus 2. And what might we want to do to that? Factor, and that factors as k plus 1, k plus 2 over to, oh my gosh, yet again, they match. Hence the beauty of induction. Okay, now before we flip the page, I want to just, because we've agreed on this, I just kind of want to show you an alternate way to do this problem from here, which ends up being helpful for some more complicated questions. Okay. You could have left this as k times k plus 1 over 2. And then instead, didn't we multiply the k plus 1 by 2 over 2, and it looks like this? Okay. So what we did in purple is we distributed, but what you might notice is that if you don't distribute, isn't k plus 1 a common factor? Do you remember when you factored by grouping, and if you got a common factor, can't you rewrite this using the common factor k plus 1 and then use the other coefficients as your factor as well? Okay, that's another way that we could have jumped there. Okay, so again, when you have that common factor, we're able to use that to factor that way. So that's another way we can do it. And this one wasn't bad to flesh out, right? If we distributed, it wasn't bad. But sometimes it's going to be awful to distribute, and you want to look for that common factor. When do you know when to distribute and when not to distribute? Do you see how k plus 1 was part of what I wanted? Oftentimes that's indicative that keep it in factored form, okay? Yeah.
So when we're doing the steps on the left, are we allowed to be specific? So if we're getting an equation 2 parentheses k plus 1 parentheses minus 1, are we allowed to just simplify that?
I don't for the green part, but I end up doing that for the blue part, just to kind of keep it as literal as possible. So people aren't like, you're jumping too many, you know what I mean? Like, how'd you get that? Where is that from? And so that you can really say like, look, this is my k, my sum of the first k terms. This is this, etc. Okay. So it does get a little tedious in that regard. Yeah, sure. Okay. So again, what is just completely necessary here would be what happens when n equals 1. You assume, and I'm highlighting assume on purpose, you assume that this is true for s sub k, and then you do this proof. Okay, essentially, that's the mathematical induction. Okay, okay. All right, ready for number 3? Okay, number 3. S sub n equals 1 squared plus 3 squared plus 5 squared, etc. Blah blah blah. So our rule, they tell us, is 2n plus, just kidding, 2n minus 1 quantity squared. And then our sum is n times the quantity 2n minus 1 times the quantity 2n plus 1 all over 3. You guys good with rule versus sum, what I mean by that? Okay, so let's show that it's true for 1. So 2 times 1 minus 1 squared equals 1 times 2 times 1 minus 1 times 2 times 1 plus 1 all over 3. Okay, so 2 times 1 is 2, minus 1 is 1, so I have 1 squared equals 1. 2 times 1 minus 1 was 1. 2 times 1 plus 1 would be 3, and then over 3. 1 squared is 1. 3's cancel. 1 times 1 is 1. We're in business. Okay, we can get on the first rung of the ladder. Okay, so when n equals 1, we're showing that this is indeed true. So now that we're on the first ladder, or the first rung of the ladder, let's assume we're on a random rung of the ladder, which is our s sub k. So we're going to put k into the rule for our sum. K times 2k minus 1 times 2k plus 1 all over 3. So we're on a random rung of the ladder. K, 2k minus 1, 2k plus 1 over 3. And now we're going to climb up one rung of the ladder. So we're on the kth step. Now we want to go to the next step, which is the k plus 1, k plus first, the next step. Okay, so again, I'm taking my rule 2n minus 1 quantity squared, and in place of n, I'm putting in k plus 1. So then the sum of the, if we include that term, I'm going to put k plus 1 in for n. So that's going to be k plus 1 over 2 times k plus 1 minus 1, write it like that, times 2k plus 1 plus 1, oops, all over 3. So that's our setup. And so now we want to show that if I'm on one rung of the ladder and I climb to the next, that should be the same as the sum of k plus 1. Now here's where, David, here's where I would, if I'm doing my work over here this way, I'm going to simplify these different pieces here, okay? So I'm going to say, all right, this is k plus 1. What does 2 times k plus 1 minus 1 turn into? 2k plus 2 minus 1. So that ends up being 2k plus 1. Okay. Now what about 2k plus 1? Sorry, 2 times the quantity k plus 1 plus 1. So that's 2k plus 2 plus 1, which is really 2k plus 3. And then all over 3. So I'm fine with that for the sum part. Let me get that, okay, to jump in. Okay. So let's feed 2 birds with 1 feeder. And let's simplify this guy, but also put it over a common denominator, if that's all right with you guys, all right? So I'm going to have this k, 2k minus 1, 2k plus 1 here. And then what did we say that 2 times the quantity k plus 1 minus 1 really turns into? 2k plus 1 squared. And if I put that over 3, that means I have to multiply it by 3. Okay. So I'm just combining some steps there instead of having like one thing where we simplify the 2 times the quantity k plus 1 minus 1, and then another where we get a common denominator. We can combine those together. Are you guys okay with that? Okay. No? Okay, someone shook their head. Sorry, it must have been a side conversation. It's very confusing. So we could flesh this out, but that kind of ends up being kind of a hot mess, right? This is where I'm like, maybe I could use that like common factor thing to pull out. Is there a common factor that I could pull out? What is it? 2k plus 1. And that behooves us because do you see how 2k plus 1 is one of the factors we want here? So that's kind of a nice thing. So let's do that. So let's pull out a 2k plus 1. So then here I'm left with k times 2k minus 1. And if I pull out a 2k plus 1 from here, I still have what left? Pulling out one of the 2k plus 1s. I still have 3. And I still have one other 2k plus 1 that's left. I pulled out one of those 2k plus 1s from the 2k plus 1 squared. So now I only have one of them left. Okay. So let's clean up the middle here. This turns into 2k squared minus k. And this is 6k plus 3. I could combine like terms next. And I get 2k squared plus 5k plus 3 over 3. And that's a quadratic I could probably factor. So I could use 2k and k. And I want factors of 3, where the outer inner give me 5. So I can use 2k plus 3 and k plus 1. Is that what we wanted? Does that match up? Yeah. It's in a different order, but remember, multiplication is commutative. So we should be okay there, all right? So this is a case where, yes, if you distributed everything out, you could end up factoring it like this. Oh, and if you use photomath, it does that. But that would be a hot mess, okay? So this is much nicer, that idea of pulling out a common factor, okay? All right. Questions on 3? Okay, ready for 4? All right. So let's start by showing that it's true for 1. So when n equals 1, I'm going to have 5 times 1 minus 3. And I want to prove that that's the same as 1/2 5 times 1 minus 1. Okay. So this gives me 5 minus 3. What's 5 times 1 minus 1? 4. So then I get that 2 equals 2. And again, when we're showing that it's true for n equals 1, that doesn't mean we need 1 equals 1. We're just saying when I substitute n equals 1 in, I get an equivalent statement for the rule and the sum. Okay. All right, so now I'm going to assume that S sub k is k over 2 times 5k minus 1. That needs to be stated, that assumption. We're assuming this is true then. And so then that means that S sub k plus A sub k plus 1 is going to be this k over 2 times 5k minus 1 plus the k plus first term, which would be given as 5 times the quantity k plus 1 minus 3. And then your S sub k plus 1 would be k plus 1 over 2 times 5 times the quantity k plus 1 minus 1. So we organized the information on the left so that we could set those equal to each other on the right. K over 2 times 5k minus 1 plus 5 times the quantity k plus 1 minus 3. And then this is going to be k plus 1 over 2. And then what could you turn the 5 times the quantity k plus 1 minus 1 into? Yeah, 5k plus 4 is fine, okay? All right, so I could have this as k times 5k minus 1. I could think about that over 2 plus, and then what does this whole thing turn into? 5k plus 2, okay? Now, when I go to my next step, and if I'm trying to put everything over 2, do you think it makes sense to keep this factor? Let's look. Is that a factor that we see that we want? No. So let's multiply it out, okay? Let's turn that into 5k squared minus k. And then what would happen to 5k plus 2 if I put it over 2? 10k plus 4. Beautiful. So then that's 5k squared plus 9k plus 4 over 2. And then how does that factor? 5k and k. I could do 4 and 1. And that really does match what this was, doesn't it? So I'll just write it like this, k plus 1 and then 5k plus 4 all multiplied together over 2. And you are all set there, okay? So again, in the problems, if you're wondering whether to distribute or to keep it factored, kind of look at what factors you want, and that can sometimes be helpful as well, okay? Last one is number 5. Now, this time they have it in summation notation. What is the rule that they're inferring in number 5? I cubed, beautiful. So this I cubed is the rule. And then of course, this part here is our sum. So why don't you guys take a minute and try to do this one on your own or with your group, okay? Okay, so hopefully we have this. We show it's true for when n is 1. We have this assumption that s sub k is going to be k squared times the quantity k plus 1 squared over 4. And then essentially we want to show that this s sub k plus the next term is going to be the sum of the k plus first term. All right, so down here I have k plus 1 plus 1. Do you guys see I just turned it into k plus 2 squared here? Okay, so the first thing that we'll want to do is maybe make a common denominator. And so I'll need to multiply this k plus 1 cubed by 4 in order for me to get that and combine the the numerators over one denominator. So then I see that I have, I could multiply it out, but that would be a very large polynomial, right? Notice there's something I can factor out of each term. What is the best thing to factor out of each term? The k plus 1 squared. Notice I cannot just take out a k plus 1, but I can take out a k plus 1 squared from each term. What's left if I factor k plus 1 squared out of the first term? Just k squared, excellent. And what about the second term? 4 and then the k plus 1. If you wrote 4k plus 4, I'm fine with that right away, okay? And then all over 4. So then we can flesh this out here. I have k plus 1 squared, And then this turns into k squared plus 4k plus 4 all over 4. And I'm close. I just need to factor this. Does k squared plus 4k plus 4 factor into k plus 2 quantity squared? Then we are in business, friends. And we have shown that statement, okay? So again, the technical pieces that you need in each case is you need to show that it's true when n equals 1, assume that s sub k has this specific value, and then prove that if you're on the s sub kth term and you add the next term of the, sorry, if you have the sum of the first k terms and you add the next term, that you would end up with this specific rule, okay? Those are really the pieces of induction, okay?